Okay, so I think we are now.
Well, that's 5 minutes past 3.
Mm. Okay, so I think it's time to start. Dear rock mechanics colleagues from Europe and the rest of the world, welcome to the second European rock mechanics debate. I am Leandro Alejano, ISRM VP for Europe, and I'm here to introduce this debate that I also inform you that it's being recorded and broadcasted through YouTube. European rock mechanics debates are based on an initiative by Charlie Li, which was the former ISRM VP for Europe, with the aim of get together from time to time and discuss hot topics in rock mechanics. These debates are held virtually, and each one will have two speakers with different perspective on a hot rock mechanics or rock engineering topic. Both of them will briefly present their views and discuss with the other presenters and with the audience. One of the main aims is also to collect opinions and suggestions from the rock mechanics community. This debate would not have been possible without the tireless effort of Philippe Vaskou, which organized this and contacted the speakers and will act today also as a moderator. So thank you very much, Philippe. And today we hold the second rock mechanics debate entitled What Model for What Application in Rock Mechanics, featuring Heinz Konietzki from TU Bergakademie in Germany and Johnny Sjöberg from Itasca and Luleå Technical University in Sweden. So thanks everyone for being here today. And without further ado, I give the word to Philippe Vaskou, moderator of this debate. So please, Philippe.
Thank you, Leandro. So I'm Philippe Vaskou from France. And when we have prepared this debate, we immediately understood that the title was really corresponding to a need. What model do we have to use depending on the application or the project in rock mechanics? So we will have two speakers with different views today. So the first one, Heinz Konietzki, will present more theoretical research, and that will be very interesting to see exactly what he can do. And after, we will have more, let's say, commercial aspects with also validation process. So the first presenter will be Heinz Konietzki. Heinz, after a PhD degree, an habilitation in the field of geotechnics, worked during 15 years in the industry in geotechnical consulting and borehole measurements. Since December 2005, Heinz is in charge of a chair of rock mechanics at TU Bergakademie, the well-known mining school of Freiburg in Germany, and later also director of the Geotechnical Institute. His main focus are rock mechanic lab testing, numerical simulations, of course, and practical application on radioactive waste disposal, deep geothermal energy, mining, civil engineering, as well as theoretical research on micromechanics and lifetime prediction. So, Heinz, it's up to you to present your presentation. Once again, I repeat, you have only 15 minutes. I know it is rather short, but please try to be in time.
Okay, thanks a lot for the introduction. So let me share my screen first.
Yes.
Okay, so a warm welcome to all participants from my side. It is a pleasure for me to share a few ideas about numerical modeling with you. As we all know, numerical modeling has become a standard tool in geoengineering, but also in geosciences. However, used tools and applied complexity can be quite different, as illustrated by this simple sketch. The field of radioactive waste disposal is a good example for highly advanced numerical modeling, especially in terms of multi-couplings, which goes beyond the standard applications in mining and civil engineering. In terms of the applied codes, we see that commercial codes are applied for nearly any task and at any level. But for very specific tasks and new numerical solution schemes, open source codes become important, although nearly exclusively used by research organizations and universities. I will start with a few general statements. We should be aware that state of science always is ahead of the state of engineering. And this implies that step by step, parts of the state of science will become available for engineering and will be applied in engineering. On the other side, we know that engineering practice inspires science. We should also be aware that state of science is not fully verified and only very limited validated. And this is also the reasons why a lot of tools which are used in science cannot be applied for engineering. We should also be aware that there is a big difference in computer power and also in computation time, which we have available in science compared to that in engineering. In engineering, we have to work in time and we have also restricted computer power. We should also take into account that software used in science is often not available in the industry, and that the required accuracy and detailedness in science is often much bigger than that we have to apply in industry. Some key questions. Whenever we start to apply numerical modeling to solve a geomechanical problem, we should ask at least these questions I have listed over here. And this should be done in a kind of conceptual model or conceptual modeling phase. We should first ask us, do we have a static or a dynamic problem? Because that has influence on the meshing, for instance, on the damping scheme we have to use, on the material properties we have to apply, etc. We all are aware that our nature is 3D, but on the other side, we can also solve a few problems, although very limited, also in 2D, which will save computational time, which would make the meshing easier, etc. We should also ask us, can we solve that as a continuum problem, or should we apply a discontinuum approach? Another problem is if we would apply large or small strain calculations. Very important also is to consider the database and also the stage within a geotechnical project. So is it more kind of scoping calculations where we need a weaker database, or are we involved in dimensioning where we need very detailed data? We also have to look into couplings. In most cases, we have to apply hydromechanical coupling. In some cases, in addition to that, also thermal coupling, chemical coupling, and nowadays also biological coupling. And very important for engineering practice is the usage of support elements. And we have to be aware that especially in rock mechanics, we have very specific ones. Now a short discussion about commercial codes versus open source codes. Commercial codes and especially multi-purpose code have several advantages. They are highly verified. We have an excellent documentation. We do also provide professional service. The handling is quite good, and we have many options, including also very nice integrated pre- and post-processing. We have also standard interfaces compatible with quite different formats, and we are accepted by the authorities and popular in the industry. On the other side, I see also several disadvantages. They are extremely expensive. And this is true in respect to service as well as leasing and purchase. We have no access to the source code, so we do not really know how the code is working. We have no full insight into the numerical simulation scheme. And the extensions are limited. Several codes offer possibilities to include own constitutive models, but anything has some limitations. If we look from the other side, so let me start with the open source codes. We have the advantage, of course, that we have full access to the source code. That means whenever we understand the programming, we have full insight into the solution scheme. They are free of charge. There are no limitations in respect to the extensions because we have the source code. And what is also very nice is that we have very active exchange via user groups, which are sitting at universities and research institutions. And this can replace to some extent also the very limited manuals which we provide. Such open source codes are widely used by universities and research organizations. But of course, we have also disadvantages. The handling is sometimes difficult, documentation is very limited. The provided existing functionalities are limited. Of course, we can extend, but what is existing is quite limited. Pre and post processing is either limited or not existing, so that we use or we have to use then additional tools to do this. There is no professional service. There is a higher error rate. So we have detected a lot of bugs. This is due to the fact that a lot of different people are working on these source codes and not anything is really tested in a correct manner. And we see a limited acceptance by the authorities. Now the question may arise, why do we have specific codes for geoengineering? This could be either commercial codes, but also open source codes. Why not using these very powerful multi-purpose codes? And here I have a few arguments. First is that we need specific constitutive models for soils and rocks, and they are often not available in these multi-purpose codes. We also need very specific elements to simulate support, like anchors, piles, etc. We also need some specific meshing tools designed for typical applications, which is provided in these specific geoengineering tools. We also need specific algorithms, like the classical shear strength reduction technique, which is now available in nearly any of these geoengineering tools. The handling is manageable and the costs are acceptable. They are much cheaper than the multi-purpose codes. And geoengineering support is offered by several of the companies who provide these codes, which can also be quite helpful. What are the major trends I see? The first is the multi-scale modeling. That means that we go from the micromechanical aspects to the macromechanical one. This is mainly done by sub-modeling techniques. Then we see an ongoing trend to high-performance computing or cloud computing. Some of the codes can also use the graphical processor units. We see an automatic coupling between mesh-based method and mesh-free methods. 3D visualization is going on. And very important is the integration of numerical models into geographical information systems, and especially nowadays also in the building information modeling technology. We see also a coupling with optimization tools and artificial intelligence, and I will speak soon a little bit closer about this topic. We see also an ongoing integration of time-dependent and time-independent damage mechanical or fracture mechanical approaches into the classical elastoplastic ones. And very important, we see also an ongoing trend in scientific computing, especially Python scripting. is very common now, because we have a lot of script available which can be combined with the numerical simulation tools. And of course, an ongoing and deeper coupling with different elements. A few words about optimization tools, etc. If we look into a geotechnical problem, we have typically at least 10 or maybe up to 100 different parameters we have to consider, and all of them follow certain probability functions, which is true for rock mechanical parameters, for the initial and boundary conditions, for the geometry, for support parameters, for hydraulic parameters, and maybe others too. And therefore, a few key questions arise in terms of this optimization, etc. The first is, to what extent influence the individual input parameters the results? This can be answered by a sensitivity analysis. What are the important input parameters? What can be neglected? Can also be answered by a sensitivity analysis. How does uncertainty in input parameters control results? Uncertainty analysis. How stable are the results if input parameters vary? Can be investigated via robustness analysis. What are the optimum parameters for design? Can be answered by optimization. And we can also use inverse optimization to back analyze the input parameters based on observation or measurements. And here the simple example how we apply these optimization tools. Just by have a combination between a master software tool and a slave. The slave is the numerical tool and the master tool is the optimization tool, where we have to define a target function, and according to this target function, this master tool creates the input parameters, which are transferred to the slave, to the numerical simulation tool, which performs the simulations, and the output is then transferred back to the master tool. And within this loop, we can obtain optimization or optimized results, or we can perform optimization. We can also perform robustness analysis or sensitivity analysis. And this has, to a large extent, replaced the more classical parameter study. Another topic is the question continuum versus discontinuum.
You have 2 minutes left, please.
Okay. So we have continuum codes, we have quasi-continuum codes, and we have a true continuum codes. And what is really appropriate depend on the scale, the task, the properties, and also the problem if we consider large or small deformations. And here we see the classical sketches. You are very familiar with that, and you see that the representative elementary volume is the key topic we have to consider. What are the new, very advanced numerical simulation techniques which are under development, especially at the universities? Coupling of different techniques or codes, XFEM, phase field method, and numerical manifold method, and further development of the meshless methods. Last slide is this one, verification versus validation. And here I would like to mention that the developer of the code are responsible for verification, because this considers the correct mathematical physical implementation. But the user is responsible for validation. That means he has to prove and to check that the underlying model represents the physical process in a correct manner. Okay, thanks for your attention.
Llega al final de la
Thank you, Heinz, for this very, very clear presentation, especially with the listing of the initial problems when starting or when looking or searching for a model. That's very clear. I'm sure we will have questions, but it will be after the second presentation. So now, Johnny Sjöberg will make his presentation. Johnny is a rock mechanics engineer with more than 30 years of experience in consulting, operations, and research. working on the underground and surface mining rock mechanics, civil engineering, tunneling, numerical modeling, of course, and rock stress measurements. Johnny is currently the general manager of Itasca office in Sweden. We all know Itasca and the codes developed by this company specialized in modeling and consulting. We all know at least 1, 2, or 3 codes coming from Itasca. We will learn more about these codes during the presentation and how to choose them. Johnny is also appointed adjunct professor in rock mechanics and rock engineering at the Luleå University of Technology in Sweden. So the title will be of Johnny's presentation will be Principles, Capabilities, and Strategies for Choosing Models. This is for you, Johnny.
Thank you very much, Philippe, and thank you, Heinz, for the first talk here. So I'll just skip over. I will be a bit more coming from the practical side and maybe a bit of the engineering side also. But first of all, we need to ask ourselves, why do we do any model? And a model has to be an approximation of reality. Otherwise, it wouldn't be very useful. And we can do this analogy with a map. If you have a map to orient yourself, if the map was in scale 1 to 1, it wouldn't be very useful, wouldn't it? So I'm taking the opportunity to quote Peter Kundal. I think Peter was in the audience also. I hope you enjoy this. We build models because the real world is too complex for our understanding. And if we build models that are also too complex, it doesn't really help. So we need to know what aspects of geology or other things that we need to include in the model. So the trick here is to choose what and how to simplify models, because we can do almost anything. I think Heinz outlined this quite well also, so I'm not going to dwell too much on this. But we can do anything from continuing with very advanced material models to something called macro discontinuum with joints included, or even in the smaller scale where we almost on near grain scale at least of the rock and look at how things behave. And in terms of capabilities, again, Heinz outlined this very well. There are some clear trends. Some of those that maybe not mentioned by him are also large models, and really large multi-scale models. They include both town scale and whole chambers or entire mines. So on the left-hand side here is a global mine scale model with a hybrid mesh including all geological structures. On the right-hand side is a local model with an ore pass group and towns and drifts around that. But these days we can even in many cases include those in the same model. So with a discretization, a resolution ranging from half a meter, maybe even decimeter, up to model sizes of 1,000 meters or more. So that's a clear trend, and we do this because we can now. Coupled models. Well, of course, the usual hydrogeology mechanics coupling becoming more common, full thermal hydrochemical mechanical coupling, but also material flow and mechanics, and coupling these together. And this is a big trend in mining and all cave mining specifically. And just an example, we can do very well today discontinuum material flow models, even in 3D. But we can also, from the last few years, couple this with mechanical modeling of caving, where you calculate stresses and deformation. So you have the draw and flow calculation in one program, you calculate stresses in cave propagation in another program, and these communicate with each other. And by doing that, we can account for all of these phenomena associated with both failure in rock mass, failure induced by flow, production changes in the mine, and so on. We have faster models, so the turnaround time is much shorter these days, even for these large models. And we're approaching something that may be real-time modeling. So when we have a change in a tunnel, it's being replicated in the model almost directly. And then there's the trend of machine learning, primarily for interpretation. I think there are some things we need to be wary about, though, with machine learning, and I'll come back to that a bit later. So how should we choose? This is another quote from a paper by Jing and Hudson, essentially saying that today's modeling capability, and this was 20 years ago, but it holds true today also, it can handle really large-scale complex equation systems, but representing the physics of fractured rocks is still questionable. I think there's been a lot of progress in the last few years also towards this, but there's still unknowns and uncertainties that we need to address. So if you think about what principles we should apply here, and this may be evident to many of you and obvious, but it bears repeating. Any choice of model should be based on representing the important mechanisms and the mechanisms in the correct scale for your problem. So just an example, you've probably seen this figure. It comes from Hook and then later adapted by Diedrichs and Kaiser and so on. We have failure mechanisms as a function of stress and rock conditions, ranging from low in situ stress to high, and from massive to more fractured and highly fractured rock. And this would cover both continuum and discontinuum behavior, but also different material response, from elastic at some point, moving on to plastic brittle, plastic ductile, or combinations of brittle and ductile behavior within the rock mass. So it's important here to choose the model tool, the material model, based on the mechanism. So you need to have some kind of sense and anticipation of what might happen before you start modeling. And we should always start simple. To build a simple model first, make sure the mechanics in that model are correct and that the results are what you think they should be. If they're not, it will not help to build a more complex model. You will only confuse yourself. So understand the reason for behavior first before you move on and add more features, make the model more complex, more reliable, and so on. And do that stepwise, of course. So we're sure that every time we add something new, it makes sense before we move on. Just an example, if you go back in time, 40, 50 years, there were no models. You had to rely on stress optical models instead for calculating stresses in pillars, for instance. So these are just two different examples of pillar stresses derived from stress optical models. But again, this is also based on mechanics, a belief that the pillar would behave linear elastically, and you can do this, and you can assess whether this is correct. And then you moved on to 2D elastic stress numerical models with the benefit of quantifying the stress, not just the flow of stress, but also levels. And then moving slowly over to the third dimension, but first doing 2.5D models where you can look at sequencing within the modeling plane, but still elastic. And then today we are at doing this in 3D. So we can model really, really large scale pillar arrays. We can model non-elastic with self-emergent fracturing within the pillar. So a plastic softening or hardening model. But again, it has to be based on mechanics. I'm using Peter's quote again. There's an art to using software tools correctly. It's not just a case of plugging in the data and hitting run. We need to understand the underlying physics and whether the model properly represents it. So physics and mechanics remain important. The useful models are those that represent the correct mechanisms. I think we all can agree on that. Sometimes simple is better, but don't expect the linear elastic model to be suitable where you think there should be a lot of yielding and plastic deformation. Then you're just fooling yourself. I think machine learning can be very useful for helping repetitive tasks and increasing interpretation. But I think the human eye and mind are more important tools for interpretation. We need to understand what's going on. We need to be able to convey that to our clients, our students, the science community, and so on. But we can save time by using machine learning. And that time that you win through any computer use, we should use that to look more at the results, interpret them more, understanding them more, and spending more time in the field. And then we need validation. I'm very happy that Heinz touched upon this also. It's a favorite topic of mine. And just to reiterate, verification is that you build something right. So it represents mathematics. Validation is that you build the right thing. So it represents reality. And calibration, which we do all the time, it's adjusting parameters until there's agreement with observations. So calibration is neither verification nor validation, but still required. You can illustrate this like this also. You have your mathematical model, you verify it to have a computer model, and then you validate it against the reality. So verification is or should be done for all numerical codes as part of code development, and often compared with analytical solutions. Calibration, really common in our business, where we have data-limited problems. So this is necessary to make our models more reliable. It's often subjective. We don't have good criteria for when a calibration is acceptable or not. And it's often case specific. So if you calibrate it against one set of conditions, it may not work for another set of rock conditions. So this is where I think we need some improvement also. And then, validation. I would say this is much less common. And the main reason is the lack of enough field data to do a validation. And still we need to do that on many different scales. I'll show you just one example of how this can be done. This is from a simulation of a mine, a large caving mine in Sweden, where they do mining with subsoil caving, and you end up with large cave craters on the ground surface also. So obviously it's really important to be able to predict where does that caving develop. Just a figure showing the ore body is really complex, truly 3D geometry. So what was done here? Well, we had observations from the ground surface. So all of these, the black lines here are observed cave cratering. The purple and red are new cave craters and fractures on the ground surface. And the gray is predicted caving and fracturing from the model. So this is a calibrated model. So it was calibrated against a range of years. And you see overall quite good agreement. We follow these development of fracturing and cave cratering. So we're quite happy. This is a well-calibrated model. But is it validated? No, not really. So what was done here was to calibrate against one set of data, observed cratering, and try to validate against measured deformation. So it's a different data set and different values. Black measured data and orange are data from the model. And although there are some discrepancies here, you see that the overall trend is quite good. There's fair agreement here. And where there's disagreement, well, that's a clue where we should look close into the model. Maybe there's some feature missing. maybe there's another structure, maybe slightly different rock conditions. So I want to say with this is that even if you do partial validation, it's also valuable. But similar to calibration, we need to develop acceptance criteria for when validation is, good enough. I want to finish off with a vision for the future, where we have a numerical model that is a mathematical copy of the rock mass. The rock is described in near grain scale with simple contact models. Any rock mass behavior is self-emergent from the model, and these models are validated against field observations and/or measurements. So the model scale then ranges from the microscale, centimeters, to thousands of meters, and we cover everything there, even reinforcement elements to drift tunnel scale and mine scale. We run these probabilistically to account for any remaining uncertainties we have in characterization, but also to replicate phenomena that are not deterministic in nature. And they're run in what I call near real time. So both static and dynamic calculations are done really fast, range of minutes, which means that you can automatically update geometries when something happens in the tunnel, when it develops, or something happens in the mine, and you get results back almost immediately also, which would help the engineers, the operational crews on site with feedback. Or is this an unrealistic dream? I'll leave you with that question, and thank you very much.
Thank you, Johnny. Thank you for this interesting presentation covering a lot of various aspects. First of all, I have a message to the audience. If you have questions, please use the discussion box, and I will receive the question and ask them to the presenters, to the speakers. I will start first. I have a question to both of you. I think, if I remember well, Johnny, you said start simple in your presentation. Would you both have an advice regarding the use of 3D versus 2D? I mean, in other words, do we have to start every time in 2D before going or switching to 3D model?
I would say no, because it can be very misleading starting in 2D if it's really a 3D problem, and vice versa. We hear that sometimes from clients that say, you need to build a 3D model, but in reality, some of that model, that problem can be addressed in 2D instead. So it depends on the problem, in my opinion.
Yeah, I have the same opinion. It is really depending on mainly on the weak elements or the driving elements, which really feature the behavior. And if we have, for instance, the orientation of the joints or faults in respect to the stress field, if they are aligned, and if we have several faults with different or fractures with different orientation, then we really have to use 3D consideration.
Okay. Well, I have a question from Mateo Garcia. Any comments on the benefits of FDM against FEM? FDM versus FEM.
Okay, maybe I can give an answer. In principle, the difference is very small. The main advantage I would see in finite element method is that we have a function which allows a nonlinear interpretation or interpolation of the stresses and deformations across the elements. But you can compensate this if you use a finite difference method with a finer meshing. And I think it is more important to distinguish between explicit and implicit methods when compared finite differences and finite elements.
Mhm.
I agree with Heinz. It's not much of a debate. We're in agreement on a lot of things, but I think I couldn't have said it better myself.
I have another question from Marco Arietta. Calibration with the current radar or INSAR data, how you consider this is worldwide accepted for model calibration?
Absolutely. It's very commonly used for, especially for open pits, but also for other surface phenomena. I would say it's well accepted. I think some of the issues here with using INSAR is understanding that INSAR is a relative measurement technique, which is different from GPS or photogrammetry or anything like that. So that you have to take in consideration, but it's more a measurement issue than a modeling issue, in my opinion.
Yeah, I agree with that. We are also using INSAR data. We only have to take into account that geodetic measurements are more accurate. So if you really want to have answers in respect to very small deformations, then you can use geodetic data. But otherwise, if you want to have an overview about a larger area, so the INSAR data are really excellent.
You know, very often we consider, and especially in the industry, that the problem of open source codes, the major problem is the lack of documentation. Bugs, of course, but essentially a lack of documentation, because young engineers have to discover almost everything. So how do you imagine solving this real issue, Heinz?
Yeah, I think this is really a problem, because the young engineers or students or scientists are working for a relatively short time on the code. So we add something, we can test this only to a certain point, and then we will leave. And documentation is very weak. But I have also good experience, for instance, with the code Jade. And there is a very nice user group. That means that you have a network of scientists worldwide, maybe 50, 60 people who are working intensively with the code. And if you join this group and you make some improvements or developments, you can exchange your knowledge with them. And this is really helpful. And you get an answer maybe overnight in most cases. So this can replace, at least to some extent, the documentation. Nevertheless, we should be very careful, because these codes have a lot of bugs inside. This we can also be aware of. So you really have to test by yourself all the different features.
Yes, sure.
Can I ask you a question also in relation to that, to Heinz?
Mm-hmm.
You mentioned during your presentation on open source codes that they're also cheaper, which may be very important for research and so on. But are they always cheaper? If you count the time, extra time needed for that, wouldn't that also be a disadvantage sometimes? Yeah,
that is absolutely right. You are right. But this is not so important if you apply this in science, where we have a little bit more time to work on that. So universities, they always have the problem to afford the money to buy the license, and therefore we switch to the open source codes. And there is also a general philosophy that universities and research institutions should prefer open source codes. Nevertheless, you are totally right. If I account for the time, then the balance may be different. Yeah.
Yes. Okay. Another question from Zhao Zihong. Could you please give more details on the criteria of validation? I do agree that validation is very important, but there is no common accepted criteria.
Exactly. That's my point. There are no commonly accepted criteria. And I think this is something where it would be really good to do some research.
Yeah.
Come up with guidelines for acceptance criteria for validation. It may be different in different situations, but right now there's not much out there.
Yeah. It's really also depending on the task. But what we could recommend is whenever you apply a constitutive model or a certain kind of coupling, then you should apply quite different boundary conditions. So for instance, if you apply a constitutive model to investigate the failure mechanism, then you should apply tensile load, shear load, compressive load, isotropic, anisotropic stress conditions, etc. So that you stress the material in a quite different way. And if you get always, or more or less always, a good answer, no? Then you can be more and more sure that your model may be appropriate to duplicate the reality.
Yes.
So what we often see in papers is that you just use a simple uniaxial test, and if you can reproduce the stress strain curve, then we say, okay, it's validated, it's working. But maybe it's not working if you use the same constitutive model and you make a tension test. And this is what I mean, that we have to really apply different conditions.
Yeah, okay. Another question from Edward Button. How do you see the ability to assess anisotropic elasticity and especially failure processes developing in numerical modeling? The anisotropy in the ground, whether textural or discontinuity based, is so important in the development and stabilization of failure development.
I mean, there's lots of material molds that can mold anisotropy, both elastically and plastically. But I guess the question is how to, I'm not sure what the question is. I mean, it would be easy to do that, but the problem is how do you get the parameters to such molds?
Right.
Take the simplest case of transverse isotropy, where you only need 5 elastic constants. Still getting those 5 is not easy. If you went to full anisotropy, then you have 9 elastic constants, and then you will have plastic anisotropic parameters also. I think that may be a large barrier to using those more these days.
Yeah, I fully agree. We have already a lot of existing models which are quite complex, but the determination of the parameters also at the different scales is extremely complicated. Mm-hmm. So I think the limitation is not the available model. The limitation is more to get all the data to get them running in the correct way.
Yes, 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 and especially, well, we all know that the quality of the results, whatever the kind of model, is the quality of the input data, of course. Because if we have very low quality input data, it is impossible even when using a good code to find something that works well, of course.
Therefore, when I can add one point, therefore we often use the sensitivity analysis, where we run the model with different parameter distributions, and we look how the different parameters influence the result. And then maybe we can detect what is very important, and maybe some of the features we can really neglect in specific cases, so that we can reduce the number of parameters we have to determine accurately.
Okay. Thank you. Well, another question from Marco Arietta. With the current huge availability of tools to model, the new generations of engineers are losing the interest in, between brackets, field work and experience. In your opinion, how, based on your experience, can we encourage the new generations to validate the model based on the real ground behavior? That's a nice question.
It's a really good question.
Yes.
And we see this trend also, and that people get stuck in computer models and not really knowing what the reality is. I think we all have a responsibility here, but I think some of this falls onto universities also. I know many universities, maybe it's not like that in your case, Heinz, but they've been cutting down on field trips and visits and all that because it is expensive. It takes a lot of time and effort. But if students aren't exposed to tunneling and mining during their study period, it will not be easy for them once they start working.
Yeah, but my experience is also that the students are asking for excursions. We want to see the field. We want to make experience. We want to go to the laboratory and perform tests. And this is something we really strongly support. So for instance, whenever we use numerical modeling or we do the lab testing, we always try to combine them. So perform a test and in parallel run a numerical model and look how it works, how you can exchange data, what you can learn from the test, what you can learn from the numerical model, and things like that.
That's very important what you say, Hans, because it shows the students or the young engineers the difficulty or the difficulties we have to get the data, for example, in a lab, because it is not that simple.
Yeah.
That's a very good approach.
I would also like to say that, I mean, sometimes I have problems because students, I mean, either they focus lab or field or they focus simulation. So, I mean, I've worked a lot just in the frontier between those two fields. And I think it's important that the people that make simulations go to the field and also that the people that goes to the field see simulation. So they can find, you know, a final agreement which will be closer to reality. I don't know what you think about that.
Now, our experience is also that the students, if we do the master thesis, for instance, quite often go to companies, and when we get a specific task from engineering practice, so maybe a pillar dimensioning problem or a slope stability problem, so that means that we collect the data from the field. Then maybe we perform in addition a few lab tests, and then we set up a numerical model, and then we can compare model result predictions with a model or back analysis with the reality. And they really prefer this. They like this more than just working on a pure, more or less theoretical topic.
Well, I have another comment from Edward Button, who previously asked about validation. Validation, key is what we actually document during construction when we do start to monitor. How well do we capture all the real processes involved?
I think that's a really good question. I think in many cases, we don't do enough measurements. And some of that may be from cost perspective, but this is also where you can use models in advance to investigate through parametric studies, for instance, what is the important things here? And then focus monitoring on those things also. And you even build an expectance model. This is what the measurement should show. You install your measurement and start comparing with that. And that will really help increasing the understanding also.
Well, another question from Rami Abu Sleiman. Do either of the panelists see the development or expansion of existing empirical and analytical methods beyond their limitations using validated or verified numerical models? Do they see this is a viable way of tying the practical engineering with the state-of-the-art science, or is this moving backwards from the numerical world, considering more problematic than the traditional use of analytical, empirical to validate, expand the numerical?
I mean, the major problem is that for most of our real problems, we will never find an analytical solution because the nature is too complex. This is the major problem. Otherwise, of course, analytical solutions are perfect, no? Because they give the correct answer and they are scale independent. But the main problem is really, especially for coupling, for inhomogeneities, we will not be able to find an analytical solution.
Okay. From the audience, I have no other comment or question. Nothing from your side, Leandro?
No, not from my side. I don't know if they want to conclude something, both of the speakers.
Yes, so we
Kind of wrap up.
We can stop the session. Thank you so much, Heinz and Johnny, for your two very interesting presentations, and also for the discussions we had right after, which are also very useful for practitioners, because this is the real interest of this kind of debate. So thank you so much, and I give you the Leandro, a final conclusion or something like that.
Okay, no. Okay, yeah, I can close here. Just thank you everyone for being here today, especially to the speakers and to the moderators. So I hope to see you soon in Finland in Europe 22 once we start to overcome from COVID. Also, I would like to say that if anyone in the audience has any idea or a proposal for a future debate, we will be happy to listen to him, because we're starting to plan for the next debate. And well, with this, I just want to close this this second debate, European rock mechanics debate, which I think it has been extremely interesting. So thank you all and have a nice day. Thank you.
Thank you.
Okay, goodbye.
Thank you.